electronic communication, sorry, electronic circuits today. So once again, I would be take a quick look because we have taken this topic yesterday, but not ended this. So quick look of this dual slope ADC, and then whatever the description is remaining, we have to be covered today. So we will be covered ADC today completely, and in the next lecture we will be move for the PLL. Okay. So we have seen that in a dual slope type ADC, integrator generates the two different ramps, one with the unknown analog input voltage Vi as an input, and another with the known reference voltage minus Vr. That's why it is called as the dual slope analog to digital converter, because it would be converted the analog signals into digital one by comparing the two voltage, that is one on the unknown input voltage, another is the reference one. And for that purpose we have taken a 4-digit decade counter, and initially it is reset to the 00. That is the diagram, logic diagram I have shown yesterday to you, where we have discussed the operation of the dual slope A to D converter. So if you have to be see the operation of this particular dual slope A to D converter, so you would be found that there is a switch where there is a two inputs are, this switch would be switching in between the two inputs. One is the reference input voltage minus Vr, another is the analog input voltage Vi. Okay, and this input is given to the one of the input of the integrator circuit, that would be nothing but a ramp generator. So it would be generate the signal that is having the ramp signal. So there is a feedback capacitor as per the structure of the integrator is there, and the resistor R is there, and it is connected. This analog input is connected to the inverting terminal. So obviously the output of the integrator or ramp generator would be a negative one. So Vs would be a negative one is there. But this output of ramp generator is given to the input of the comparator circuit, and again in the inverting terminal, the resulting output of the comparator would be positive one, that is Vg. And the output of comparator along with one clock signal is given to the AND gate. The output of the AND gate is act as a clock signal for the 4-digit decade counter, and the output of the decade counter according to the count up and count down, this count would be detected by the count detector, and that is for the duration of t1 second, and output of this count detector is used to control the control circuitry, and the output of control circuitry is again fed to the switch. According to that, switching operation would be changed from analog input voltage Vi to reference input voltage Vr, and this process would be continued. And control circuit would be also used to latching and display of the 7-segment decoders. So we would be see all this operation here. So if you have to be consider the operation of the dual slope A to D converter, so assuming that 4-digit decade counter is initially set to the 0 0 0. So it is initially we have set it to the 0 0 0 and 0, because we are taking the 4-digit decade counter here. So the ramp output Vs is reset to 0 volt initially. Analog input voltage is then positive, we have to be considered, and input to the ramp generator or integrator is switched to the analog input voltage Vi. So according to these assumptions, we have to be start with the positive analog voltage. It is connected to the inverting terminal of the integrator, and the integrator output Vs would be a negative one, negative ramp signal, and this negative ramp signal is given to the inverting terminal of the comparator. So resulting comparator output would be a positive, and the clock signal is passed through the AND gate, and this results in counting up of the 4-digit decade counter. So if you have to be see, it would be up by the one more count, and then again the switch would be switching from VI to VR. We would be come to this point, but before that we have to be discuss what happens in the first condition when the positive analog voltage is applied and what type of the output would be generated. So this is the dual ramp output waveform. So if you have to be see initially when positive analog voltage is applied to the integrator input, so you have to be generate a negative ramp VS. There is negative ramp signal. So you can see here, this is the negative ramp signal is going on from the negative direction from 0 to negative side, and we have to obtain a minus VS signal. So during the duration of T1, this negative ramp will be proceed for a fixed time period T1, and which is basically determined by a count detector for the time period T1. At the end of the time period T1, here you can see in the diagram, the ramp voltage is you can given by a formula, that is it is negative minus Vs is equal to input voltage upon time constant RC, Vi upon RC into time period T1. Okay, where RC is a constant, RC is a constant, a time constant of the ramp generator circuit. Okay, so this in this way we have to be obtain this. You can give it the equation number 1. Okay, now if you have to be see this ramp output waveform, or you can see the counter circuitry also. When the count reaches to the fixed count at time period T1, the count detector gives a signal to the control circuit. So you can see here, when the count detector reaches a fixed count at time T1, so this count detector gives a signal to the control circuitry, which is in turn reset the counter to the 0. If initially it will increase to the negative side, then again it would be goes back to the 0, and in this way it would be switches the integrator input to negative reference voltage minus VR. Now this switch would be moved toward the Vi to, it would be moved from Vi to minus VR. Okay, and now the ramp generator begins at start with the minus Vs, but as we have applied the negative reference voltage, so negative positive, it would be goes to the positive side. Okay, already the input is applied to inverting terminal and it is negative input, so the resultant signal would be goes to the positive direction, and Vs would be increases, ramp output would be increases upward until it is not reaches to the 0. So here you can see that it will be travel from minus Vs to the 0 volt, and the comparator output will be become 0, and because of that what happens, clock signal is inhibited from passing through the AND gate, because one of the signal of this circuit is 0. Here Vg is 0, and it is, so what happens, clock signal, so output would be not as a low output would be so here. So this clock signal initially for T1 time it is like this, and for the T2 time period it would be at the 0. So this is the time duration for the, you can say, T2. When at the, in this way you can see the time period would be completed. One complete cycle of the clock would be completed. Okay, now this conversion cycle is completed. and positive ramp signal could be defined by the equation. In this case, Vs is equal to minus Vi upon Rc into T2. This is your equation number 2. Means Vs is equal to Vi upon Rc into T2, because minus minus would become plus. Okay. So since the ramp generator voltage start at 0 volt and decreases down to the minus Vs and then increasing up to the 0, the amplitude of the negative and positive ramp voltage are equated as like this. Since the ramp generator output is start 0, decreasing to minus Vs, then again reach to the 0. So the amplitude of negative and positive ramp voltage are equal. So that is mentioned here, and you would be get a relationship between the Vi and Vr. So it is equation number 3. So minus Vi is equal to Vr into T2 upon T1. So from the above equation, it is clear that the unknown analog input voltage is proportional to the time period T2, because here Vr is known reference voltage and T1 is the predetermined time period. So also the contents of the 4-digit decade counter at the end of conversion reflects the variable time period T2. So in this way, we have to perform the analog to digital conversion with the help of dual slope ADC. Okay, so you can go with one of the example also for this case. For example, consider a frequency of clock signal is frequency is 1 megahertz. Okay, so it is 1 megahertz signal is there, and the reference voltage Vr, it is equal to minus 1 volt. Okay, and the fixed time period T1 is 1 millisecond. And RC time constant RC is also equal to the same 1 millisecond. The product of RC is 1 millisecond. So assuming the unknown input voltage Vi, we have to assume that Vi is equal to 5 volt. For this case, during the fixed time period T1, the integrator output Vs would be, what is the value of Vs in this case? So Vi is given, it is minus Vi upon Rc into T1. So it would be came as minus 5 upon 1 millisecond into 1 millisecond. So output would be, Vs would be here in the first condition minus 5 volt. And because of that, what happens? The count would be up by the decade counter for a T1 time period. During a T2 time period, the relationship is what? Vs is equal to Vr upon Rc into T2. So you can calculate the value of variable time period T2 is here. So T2 would be what? It is Vs into Rc upon Vr. So Vs is coming as minus 5 volt. It is here you would be taken it as a 5 volt as amplitude part. So it would be 5 volt. Okay, because in the case of T2 time, Vs would be goes to the positive. That we have already seen through the description. Then it is 1 millisecond. Okay, and then upon Vr is how many? It is minus 1 volt. So it would be 1 volt. We have to only take the amplitude part here. So Vs and Vr both are negative, but it would be cancelled out actually. So it would become as T2 is how many time period? It is 5 millisecond, or in terms of microsecond you can write it as 5,000 microsecond. What it means? Hence you can see the 4-digit decade counter value is 5,000, and by activating the decimal point of the 7-segment display, the display would be directly read 5 volt. So display would be show you the 5 volt, and counter value would be here 5,000. So in this way, analog to digital conversion would be performed with a dual slope A to D converter. Now we have to move to the next type of A to D converter, that is successive approximation type A to D converter. So here the conversion time is maintained constant in the successive approximation type A to D converter, and it is proportional to the number of bits in digital output. Unlike the other counter, like the counter and continuous type of A to D converter, the conversion time is maintained constant in the successive approximation type A to D converter. The basic principle of A to D converter is that unknown analog input voltage is approximated against an n-bit digital value by trying 1 bit at a time. And we have to start here with the MSB. So if you have to see this description how to conversion has been performed in the successive approximation type A to D converter, we have to start with the count or trial method, hit and trial method, and it would be start from the MSB. For example, see here the steps that we have to follow for the conversion. So A to D converter operates by the successively dividing the voltage range by the half, 1/2. And the steps of conversion is like first MSB is initially set to 1 with remaining 3 bits set to 0. We are taking the 4-bit A to D converter. The first MSB would be considered as a 1, remaining 3 bits would be considered as a 0. So the digital equivalent is compared with the unknown analog input voltage. Okay, and if analog input voltage is higher than the digital equivalent, the MSB is retained to the 1, and second to the MSB is set to the 1. Otherwise, if analog input voltage is lower than the digital equivalent, MSB is reset to 0 and second MSB is set to 1. You can see it from this diagram. If you want to note down this diagram, you can take the screenshot of this also. So this is the 4-bit successive approximation process. We have started with the 000, and initially we have to do the MSB is 1 and rest of 3 bit is 00. Now there is a 2 possibility. Analog input voltage is greater than this digital equivalent. So in this case, MSB is kept at the 1, but second MSB would also convert to the 1. And the second possibility is that analog input voltage is less than the digital equivalent. In that case, MSB is replaced by the 0 and second MSB is considered as a 1. And this process would be repeated. You can see here also. So again, this upper one is again 2 cases. First is analog input voltage greater than digital equivalent. So all MSB would be kept as it is. And next to MSB is third MSB is here 1. Similarly, in this case, if analog input voltage is less than the digital equivalent, then here we are talking about a second MSB. So second MSB is 0 and third MSB would be 1. Similarly here, the first upper case is analog voltage is greater than. So in this case, this second MSB is as it is and third MSB is also 1. But in the another case, when analog input voltage is less than the digital equivalent, so this second MSB is 0, that is 1 in the previous case, and third MSB is 1. So in this way, every branch having the 2 sub branches, and it would be going to up to the 16 digital equivalent, because there is a 4-bit successive approximation type process is there here. So there is a possibility of 16 different digital equivalent signals. So in this way, conversion has been performed, and comparison is made as given in the step 1 to decide whether to retain the or reset the MSB, second MSB, third MSB, like this, up to the repeated down up to the LSB. And by this time, the converted digital value is available in the successive approximation register. Now we have to see the block diagram of this circuitry. So this is the functional block diagram of successive approximation type A to D converter. Please note it on this diagram. So in this case, you can see that there is a successive approximation register is there, SAR, and there is a 2 control signals are there, start of conversion and end of conversion, EOC, end of conversion, and there a clock input is there, and the output of this register is a digital output, that is start from MSB to LSB, B1 to B8. Here we are talking about the 8-bit. Now it would be given to the digital to analog converter, and this analog output of D to A converter is nothing but a reference voltage that is applied to the non-inverting terminal of the comparator, and that is compared with the unknown analog input voltage, and that whatever the case we have discussed, in this way conversion is performed. Means if Vi is greater than this VR, so MSB would be retained and second to MSB would be 1. But if Vi is less than VR, then MSB would be 0 and second to MSB would be 1, and this process would be continued up to the we have not reached to the LSB. Okay, so here we are talking about the 8-bit successive approximation type A to D converter. So we have to be see with the start of this conversion. So when the start command is applied, SAR sets to MSB of digital signal is 1, and rest of it would be other bit are made 0. So trial code would be becomes 1 followed by the zeros. Here we are talking about the 8-bit A to D converter. So trial code would be here 1 7 times 0. So output of SAR is converted into the analog equivalent VR and get compared with the input voltage Vi. If Vi is greater than D to A converter output, so the MSB is retained as 1, and next significant bit is made also 1, and testing is repeated. But if Vi is less than D to A converter output, so comparator would be reset the second MSB to 0 and proceed for the next most significant bit. So this process would be repeated for all remaining lower bits in the sequence until all bit positions are not tested. So the end of conversion EOC signal is sent out when all the bits are scanned and the value of D to A converter output just crosses Vi. So this is the process that we have already seen for the 4-bit. Same process we have to be here for the 8-bit A to D converter. So this is a table has been shown how the conversion has been performed for one trial code 1 7 times 0. You can see this is the final output that is corrected digital representation. Second column is successive approximation register output, that is Vi at the different stages in the conversion. This is the trial code 1 7 times 0. Start with this, and this is the comparator output. It is 1 or 0. Depending upon that, your input to the SAR register would be given. Okay, so and that is actually the final output would be also there. So you can see start with this one. So this trial code would be compared with the analog input. If Vi is greater than this, So output of the comparator would be 1. This is the first bit of the corrected digital output. Okay. Then again, so what happens when it is 1 means next to the MSB would be also set to the 1. And then again this equivalent is compared with the VI. Again VI is greater than this. So again comparator output is 1 and this would become second bit here. So if again it is greater than 1, so the third MSB would be also 1 and remaining 2 would be remains the 1. Okay. Now this third digital equivalent will be compared with the VI. Now VI is less than this. Then what happens? A 0 would be comparator output. So because of that, what happens? We are talking here as the third MSB. So this third MSB would be now 0. And next to third MSB would be, means fourth MSB is 1 here. Okay. Again it would be compared with the VI. Again VI is greater. So comparator output is 1. So what happens? This fourth MSB would be remains 1 and the fifth MSB would be now again 1. So this process would be continue till we have not get the corrected digital representation, that is 1 1 0 1 0 1 0 like. Okay, so it is a 8-bit A to D converter. So 8 times the comparator output we have to be observed to reach the corrected digital output. Okay, so this is a very simple way that we have to be perform the conversion in the case of successive approximation type A to D converter. So we have learned all 3 A to D converter that we have to be required as per our syllabus. Now we have to see the advantage of this SAR type A to D converter. Here the conversion time is very small, conversion time is constant and independent of amplitude of analog input signal VI. But what is the disadvantage here? Circuit is complex. This is the only disadvantage you can consider here. Or you can also see there is one more disadvantage, like conversion time is more as compared to the flash. Flash is direct conversion, so it is faster than this successive approximation type ADC. Now we have to see the characteristics of the ADC. So like the DSC, there is some characteristic of ADC also there. Similar terms are mostly repeated here. So first one is the resolution. We have seen the resolution refers to the finest minimum change in signal which is accepted for the conversion. Okay. So it is decided with respect to the number of bits. So it can be defined as resolution 1 upon 2 raised to the power n for the n bit A to D converter. The n is the number of digital output word bits. The ratio of full scale input voltage to resolutions gives the minimum change of input voltage which cause a change of 1 LSB. That is delta VI for 1 LSB is VFS upon 2 raised to the power n. So this is the first, you can say, characteristics of the A to D converter. And VFS is what here? It is a full scale input voltage range. Second characteristics, if you have to be considered, that is again same point that we have taken on the D2AC, that is quantization error. So if the binary output bit combination is such that for all values of input voltage VI between two voltage levels, there is unavoidable uncertainty about the exact value of VI when the output is particularly a binary combination. This uncertainty in between the two voltage levels is termed as quantization error, and its value is maximum plus minus 1/2 LSP. That we have also seen in the yesterday lecture. And maximum number of bits selected, if maximum number of bits selected, finer the resolution is improved. If the number of bits is increased, so smaller the quantization error. So to decrease the effect of quantitation error, we have to increase the number of bits for the conversion. Third one is an conversion time. So it is defined as the total time required for an A to D converter to convert the analog signal to the digital output, and it depends upon the conversion technique and propagation delay of the circuit components. Fourth one is analog error. So it is an error occurring due to the variation in the DC switching point of the comparator, resistors, reference voltage source, ripples and noises introduced by the circuit components. It is termed as the analog error, because all the circuit is made up from the different discrete electronic components. Okay, op amp, resistor, capacitor and other things. So this would be introduce noises, ripples, such kind of the errors, that is considered as an analog error. Fifth type of the characteristics is that linearity error. So it is defined as measure of variation in voltage step size. It indicates the difference between the transition for minimum step of the input voltage change, and this is normally specified as a fraction of LSB. Another is linearity error is differential nonlinearity error. That is the analog input levels that triggers any two successive output codes should be differ by 1 LSB. Then differential nonlinearity error is 0. But if it different from any value that is different from the 1 LSB, means any deviation from this 1 LSB value would be defined as a differential nonlinearity error. Okay, and the last one, the characteristic is the integral nonlinearity error, INL. That could be represented with the help of one graph. I will show you the graph. So an actual A to D converter characteristics which with a missing code. The dotted curves would be represent the locus of the midpoints of that actual input steps of the voltage ranges, and this line is called a code central line, and the maximum deviation of the code central line from the ideal straight line passing through the endpoints of the ideal characteristics after nullifying the offset and gain errors is called the integral non-linearity error. So there is not a straightforward definition. It could be understood with the help of this graph. So here in the y-axis the digital equivalent, and in the x-axis there is an analog input voltage in equal differences or step size, you can say 1 by 8, 2 by 8, like this. So this is the solid line, straight line is the ideal characteristics, that is between two endpoints, and this is the center code line that is deviated from this particular straight line. So how many amount of the deviations between these two, that is considered as a integral linearity error. Okay, so these are some example is also shown. The missing code is there and how we have to be identified. The deviation could be maximum 1 LSB, but if it is more than this, then there is an integral error would be occur. Okay, so this is all about the A to D converter. At the end you can see the comparison. Sometimes comparison is also asked in the examination. This is important, very important point. So here we have taken the comparison of all these three that we have in our syllabus: flash type ADC, dual slope ADC, successive approximation ADC. So we have to be compared in the terms of 8 points is mentioned here: category, operation, power, noise immunity, speed, resolution, sample and hold circuit, and the cost. So if you have to see flash, it is a non-program, direct type, and open loop category that I have told you that the categorization of ADC. In ways of programming, non-programming, direct, and that is indirect or open loop or closed loop. This is the mention here. Dual slope is non-program, integrating type, and open loop. And subsuccessive approximation is program type, direct type, and closed loop. Okay. Operation if we see, flash ADC is parallel comparator arrays it is having, and dual slope is integration versus known voltage reference, and successive approximation binary search comparison. In terms of power, flash ADC would be having the maximum or highest power consumption, and dual slope is lowest, and successive approximation is medium. And the noise immunity, if you have to talk about, the dual slope is the highest noise immunity, and flash type is lowest. If you have to talk about speed, flash type is having the highest speed, fastest. Everyone please start to fill up the attendance as well simultaneously. And dual slope is slowest as compared to all these three. And if you have to talking about the resolutions, so flash is having 4 to 12 bit resolution, dual slope is 12 to 16 bit resolution, and successive approximation having the 8 to 16 bit resolution. And if you're talking about the sample to hold circuit, flash type ADC does not require this circuitry. Even dual slope is not required, only successive approximation type ADC will be required this. And if you're talking about the cost, flash type having the highest cost and successive approximation having the lowest. So these are the some points where we have to be compare these three ADCs, and that you have to be take the screenshot of this comparison. It is a very important questions from the university examination point of view also, as well as the oral during the practical. So this is all about the analog to digital converter and digital to analog converter. In the next lecture, we would be go for the topic phase locked loop, and then data converter. So 2 more lectures are required for the completion of the syllabus that would be covered in this week up to Friday. So I hope all of you have given the attendance or not. Quickly, please put up your attendance. Time is very less. I would also put up the assignment number 5 today on your Google Classroom and share with your WhatsApp group. 2 more assignments are remaining for unit number 5 and unit number 6. I would be put up on your WhatsApp group.